You probably all know Einstein's famous equation E equals mc², which describes how much energy is contained in a mass. One of the most important insights from this formula was that each atom contains an incredible amount of energy, which unfortunately also led to the development of the first atomic bomb. However, for fundamental particles there are a number of alternative equations to E equals mc², which only few people are aware of and whose meaning is not easily clarified. But before showing you these equations, I first want to introduce you to some relevant particle properties. The Compton wavelength is a property which can be determined experimentally, and it's also easily possible to define an associated Compton frequency. Dividing the Compton wavelength by 2 pi gives the reduced Compton wavelength, which I denote here as Compton radius, since this quantity behaves like a radius in the equations which will be revealed shortly. In another video, I demonstrate that using these three quantities it's also possible to model fundamental particles as rotating spheres. You can find the link in the description box. The energy of a fundamental particle with elementary charge E can then be described using the electric energy as follows. Interestingly, it's necessary here to multiply the Compton radius with the sum of the constant alpha to get the desired result. This constant vanishes if the elementary charge is replaced with the Planck charge, which is approximately 11.7 times greater than the elementary charge. Using magnetic field energy, it's possible to calculate a fundamental particle's energy as follows. This equation means that a charged fundamental particle contains the magnetic field energy of a current-carrying ring. The radius of this ring would be the Compton radius, and the current intensity is given by the multiplication of the elementary charge with the Compton frequency, whereby this frequency simply states how fast the elementary charge is moving through the ring. The magnetic energy can alternatively be calculated using the Planck charge, like in the electric energy case. The depicted formulas also contain a magnetic flux variable, which is denoted by the Greek letter phi, and states how much magnetic field is going through the surface enclosed by the ring. Since the proper calculation for the flux is unclear here, it was assumed that the use of the magnetic flux quantum is appropriate, which according to measurements seems to be the smallest possible amount of magnetic flux in our universe. Besides, I also want to add that, in order to give the desired result, the shown magnetic field equations were multiplied by a factor of 4 compared to the textbook equation for the magnetic energy of a ring-shaped conductor. Using a gravitational field, the energy of a fundamental particle can be represented in the following way. Remarkably, the particle's mass must be replaced here by the Planck mass. This quantity is astoundingly large for using it in particle physics with its approximately 22 nanograms. Furthermore, a fundamental particle's energy can also be calculated as rotational energy. This simply requires multiplying Planck's constant h with the particle's Compton frequency. Alternatively, it's also possible to use the Compton wavelengths for the calculation, or particle spin, whereby this formula was also multiplied by a factor of 4 compared to the textbook equation for the energy of a rotating mass. The equations for electric, magnetic and gravitational energy, by the way, are reduced to one of the two depicted rotational energy equations. This can be interpreted twofold. Either the electric, magnetic and gravitational energy equations are just mathematical variations of the rotational energy equations without own physical significance, or the rotation of a fundamental particle is essential for all its energetic properties. Personally, I think that the latter is appropriate. But what are the previously mentioned fudge factors for, like alpha and the number 4? And strictly speaking, the used equations for electric and gravitational energy relate to the energy of a two-particle system, which is why charge and mass are squared in these equations. I think that all this gives hints to the self-energy of fundamental particles. That is, by which amount do the stated energies contribute to the measured mass of a particle. I think it's elegant trying to explain particle mass through self-energy, since there is also no satisfying explanation on the origin of particle mass, in case you doubt the acclaimed Higgs mechanism like me. Always explaining everything by inventing more particles and more fields, like with the Higgs mechanism, cannot be expedient. The appearance of the Planck charge and the Planck mass in some of the depicted equations is considered by me as a hint for fundamental particles changing their properties in the extreme close-up range, or that their properties are shielded in some way. This, however, is a topic for another video. Additional information can be found in the description box, and give this video a like if you enjoyed it.